This is test 3, problem 1. We have a ball hanging from a spring submerged in a tank of water. The spring, after it's released from rest, will contract a little bit, and we need to find the final length of the spring. We'll start by drawing a force diagram of the length of the spring at the final position, where it is merely the gravitational force and the spring force balancing out. We can write our equation for F net because the force is in rest. We know that F net must equal 0. And it is the sum of the spring force and the gravitational force, which are both in the y direction, the negative y direction. We can show that F spring is equal to, from the formula, negative k times the compression or the stretch, which is L minus the relaxed length, again in the negative y direction. And F of gravity is simply the mass, which is m over 10 times g, also in the negative y direction. Combine these all together, 0 is equal to negative ks. Well, actually, we'll cancel this negative because it is in the negative y direction. So that just becomes positive k sub s times L minus L naught. And gravity is in the negative y direction, so that'll be mg over 10. We'll move things around so that we can isolate L. Looks like L is equal to L naught plus mg over 10 ks. Cool. Moving on. We want to find the temperature change for the system in between the two states using the transfers of energy in between. So the system in this case will be the ball, the water, the spring, and the earth. And the surroundings will just be, say, the container. Okay. Start with the energy principle. The energy change in energy in the system is equal to the work done by the surroundings. However, there is no work done by the surroundings because it says that that's perfectly insulating. No heat is lost, so nothing to worry about there. So we will separate the energy into its constituent parts. Kinetic energy, gravitational potential energy, spring potential energy, and it sums up to equal 0. No. We also have internal energy, or thermal energy. And all sums to equal 0. We can rewrite this because we need to use thermal energy to find the temperature. So we will say that E thermal is equal to negative U grav minus U spring minus K. However, K is 0 because it isn't rested at both the initial and the final states. So we can ignore kinetic energy in this example. Okay. Let's start by defining some of these terms. So the change in U grav is mass times gravity times the change in height. Mass is m over 10 times the change in height. Now, what is the change in height? Well, if we call this height to be 0 and this height to be something in between d and or 0 and d, it must be the difference between the two. So this is d minus L. Now, L was given in the previous question, so we can actually substitute L in. since L is equal to mg over 10 times K sub S plus L naught. You can say that the gravitational potential must be mg times mg over 10 times d minus mg 10ks minus L naught. Spring potential is given by 1/2 K times the change in the compression, so S final squared minus S initial squared. We can say that S final is equal to the stretched length, so L minus the compressed minus the relaxed length, so L naught. Once again, L can be substituted, so this is mg over 10 ks minus plus L naught minus L naught. These two cancel, so this is just mg over 10 ks. The initial compression is L sub I minus L sub naught, and therefore the spring potential is 1/2 ks times mg over 10 ks squared minus L sub I minus L sub naught squared. We can bring these two, the gravitational and potential energy, into our equation. E thermal is equal to negative mg over 10 times d minus mg over 10 ks minus L naught minus 1/2 ks mg over 10 ks squared minus L sub I minus L sub naught squared. Okay. We'll substitute in our coefficients for each of these parenthetical terms. We'll have mg over 10 times negative mg over 10 ks minus mg over 10 times d minus L naught minus 1/2 ks times mg over 10 ks squared minus 1/2 ks times L sub I minus L sub naught squared. We can combine some of these. We can combine and refine some of these terms. So this first term becomes 1 over ks times, since these terms are all repeated, mg over 10 squared. This term does not change. This term, however, does. We can notice that this ks in the numerator will cancel with one of the ks's in the denominator since it's squared. So we can pull that one out. 1 over 2 ks times mg over 10 squared. And again, and this term at the end also does not change. We can notice that this first term and this third term will combine. And 1 over ks minus 1 over 2 ks will just be 1 over 2 ks. And we'll bring our other terms down as well. Okay, we have that now. We can calculate another formula for E thermal based on the MCAT equation. So MC delta T for the water plus MC delta T for the ball. However, M and C are both different. They're both over 10. We can combine these terms to get the thermal energy of the whole system, and that'll just be 101 over 100 m times c delta T of the system. We can set this. We can rearrange this to isolate delta T sys, since that's what we're trying to find, and it will be equal to E thermal times 100 over 101 mc at the bottom. We can go ahead and substitute in E thermal up here. So delta T sys must be equal to 100 over 101 mc times our entire equation from before. And that is done.